Okay, let's start again. My name is Fangda. I worked with my partner Laura and Andre. We worked on localizing the Aurora using the ISS time series. So there's a simple Nikon D3S that's attached to the bottom of the ISS that takes pictures of these auroras as it flies over the Earth. So the main problem is that we have to use these time series as a low-cost method to determine the camera orientation and extract where these auroras you see, where their coverage is on Earth. So whenever you have this kind of spatial orientation problem, you do a brute force algorithm, right? So that was the nice thing to do. So on the right side, you just implement a simple star centroiding algorithm. And on the left, you start with some database of known stars, and then you do a simple least squares calculation. But the problem is that as we flick through these, so I'm just varying my 3D grid in the orange stars, and my data points are the yellow. And you see that your grid size has to be much smaller than the average interstellar spacing. And this means that more than 10 to the 12 image centers must be searched, and you have to perform 10 to the 12 least squares optimization problems. And this is obviously not possible. And the data is too poor for intensity data to be used in the image, so it really requires a more refined method. So that's where our second attempt comes in, and that's the incorporation of the time domain information. So the ISS follows a known orbit. You can find it anywhere online, so you can get the ephemerids of that. And so the ISS has its effective rotation axis shown in blue, and the direction of the ISS velocity is just given by the time derivative of the nadir. So depending on the orientation of your camera, which is shown by the orange arrows, and relative to the velocity of the ISS shown by the red arrows, you see that there's a difference in the relative velocities of the stars on either side of the image. So as you tilt the camera towards 90 degrees, you see that in fact the stars rotate around the effective ISS revolution axis. But I'll hand off the mic.
All right, so now we looked at how we could actually pull, basically using star trails, how we could pull the location of these images out. So as we mentioned, if you look at a star on the horizon and it goes up at a certain speed, and over a certain period of time, you know how far it's going to travel. As we get towards the poles, that distance is going to get smaller, and so the idea is to use that information with the virtual pole of the ISS to find out where we actually are looking. So the orientation via star trails, the first thing we need to do is we need to do some segmentation. We do kmeans segmentation, which is basically a Gaussian clustering method, to remove out the Earth so that we get just the stars and we figure out where the horizon line is. This is just an image of the kmeans segmentation. So you can see we also figured out where the aurora is based on the segmentation algorithm. So then what we do is we compute these star trails. So we extract the stars by just looking for basically we isolate the stars in each image, and then we add all the images together from 1 minute of footage, from 60 frames of footage. Each image is taken every second. So this amounts to basically 1 minute of star trails. And you can see in the parts of the image that are closer to the equator, you get a longer trail, and parts of the image which are further from the equator, closer to the virtual pole of the ISS, you get a smaller star trail. So we can use that to figure out where the angular position of the stars are on the image. So from that, we can basically triangulate backwards to figure out where where the stars are in the image, where the virtual north pole is. That gives us the position that our image is looking at, and then from that we can pull out where the field of view is on the Earth, and then by extracting the aurora, we can then reposition the aurora back over top of the field of view on the Earth. And all right, thank you.
That's great.